Okay, let's take a deep breath and begin our descent, shall we? Welcome to our latest explainer. Today, we're taking a high-tech look at the invisible, physical mechanics of the ocean. We're going to look right past the fish and the coral and instead look at how pure energy actually behaves when it hits the water.
Think about these two mysteries for a second. First, why is the ocean blue? And second, how exactly do whales manage to communicate across literally thousands of miles of seemingly empty water? To answer these questions, we really have to stop thinking of the ocean as just a giant swimming pool and start framing its immense density as a unique, almost alien medium that we need to decode. The way energy moves down there is entirely different from how it behaves up here on land.
So here is our roadmap for today. 1. Decoding ocean energy. 2. Heat transmission in water. 3. Light and ocean colors. And 4. Sound and the SOFIR channel.
Let's jump right into part 1, decoding ocean energy, a high-tech scan.
And that brings us to part 2, heat transmission in water, an insulated surface. To understand heat in the ocean, we first need to quickly fire off the 3 ways heat is transmitted in physics. First up, we have conduction, which is the increase in molecular movement from nearby fast-moving molecules. It's like leaving a metal spoon in a hot cup of coffee. It heats up. Second is convection. This is driven by changes in density, where warmer, less dense water rises up and spreads the heat around. And third is radiation, which is just the direct transmission of heat from an energy source, like the sun hitting the earth. Now, here's the really wild secret about the ocean. When it comes to conduction, water is incredibly stubborn. It is actually a surprisingly poor conductor of heat.
And that stubbornness brilliantly illustrates why the ocean's heat doesn't easily sink. As solar radiation blasts the surface of the ocean, it warms up that top layer. Now, because warmer water is less dense, it naturally just wants to float right on top of the colder water below it. Combine that with the fact that water absolutely refuses to easily conduct its heat downward, and the result is that the heat just hovers right at the top. You know when you're treading water in a lake during the summer, your shoulders are nice and warm, but your toes are freezing cold? That is exactly this principle in action. Unless there's active seasonal mixing or upwelling, that warm layer stays stubbornly trapped above the much colder depths.
Moving on to part 3, light and ocean colors, the ultimate filter. So while the sun bombards the Earth with a massive electromagnetic spectrum, gamma rays, X-rays, ultraviolet, infrared, only visible light actually manages to transmit into the water. But it doesn't last long at all. This is due to a process called attenuation. It's a fancy word, but attenuation is simply the decrease in light intensity as you go deeper. It's affected by suspended particles and little organisms in the water, and scientists actually measure it using a really simple device called a Secchi disk. Get this. About 60% of the light that hits the sea surface is absorbed in just the very first meter. By 10 meters, 80% of it is completely gone.
And then we hit this number, 1,000 meters. Below 1,000 meters, absolutely zero light penetrates. The attenuation is total. This plunges the vast, vast majority of the global ocean into a permanent pitch-black darkness. But let's look at the light that actually does make it, because this answers our initial question of why the ocean is blue. Visible light is made up of different color components, right? From red, which has the longest wavelength, all the way to violet, with the shortest. Well, water acts as a massive selective color filter. It strips away the longest wavelengths, the reds, almost immediately. Then the yellows, then the greens. The blue wavelengths are literally the only ones capable of piercing the deepest into the water column. And that is exactly why objects and the ocean itself tend to look so vibrantly blue underwater. And this filtering effect explains a whole lot when we compare the crystal blue open ocean against nearshore environments. You've probably noticed that coastal waters often don't look blue at all, right? They look kind of green. That's because nearshore waters carry a heavy load of suspended particles and living organisms. These particles reflect different wavelengths of light, specifically green, and they increase the overall light attenuation, which creates that murky greenish hue, rather than the deep clear blue of the open ocean. Now, light doesn't just fade in the ocean, it also bends. This is a concept called refraction. Because water is so much denser than air, the speed of light actually slows down when it hits the water. This sudden change in speed causes the light rays to bend at the exact moment they enter the sea surface. Think about looking at a simple glass beaker. An object at the bottom isn't exactly where it appears to be from the surface. The degree to which that light bends is affected by both temperature and salinity. Basically, the denser the water, say the saltier it is, the greater the refraction.
And because of this highly predictable bending, oceanographers can easily measure water salinity using a specialized optical device called a refractometer. All right, let's dive into our final section, Part 4, Sound and the SOFAR Channel, the Deep Acoustic Highway. I want you to contrast these two environments starkly for a moment. Sound absolutely tears through water 4.5 times faster than it does through the air we breathe. Water's incredible density, which makes it such a tough barrier for light, actually makes it a spectacular conductor for acoustic energy. When sound hits an object underwater, it reflects right back to the source. And because low-frequency sounds dissipate much, much slower than high-frequency ones, they can travel incredibly far. This physical reality is exactly what allows marine mammals to use echolocation to find prey. It's also how human ships bounce sonar pulses thousands of meters down to the ocean floor to measure distance, navigate, and essentially map the total darkness. But here is where it gets really interesting. The speed of sound isn't uniform everywhere in the ocean. It fluctuates. Let's break down the precise physical variables that dictate acoustic speed. The speed of sound in water increases with 3 things: increasing temperature, increasing pressure, and increasing salinity. Now, salinity doesn't really have a constant trend with depth, so it's a bit less important for a vertical scan here. But temperature and pressure, they change drastically as we drop deeper into the water column, and they dictate a truly fascinating phenomenon.
Let's map this out carefully, because it's a bit like a giant puzzle. Near the surface, the ocean is warm, which means the speed of sound is relatively high. As we descend, the temperature drops rapidly, which causes the speed of sound to decrease. However, as we keep going deeper, the pressure of the water above becomes absolutely crushing. Eventually, that increasing pressure overrides the effect of the cold temperature, and the speed of sound starts to increase again. This creates what we can call a squeeze, a specific zone right in the middle of the water column where the speed of sound hits its absolute minimum. And this brings us to the climax of our descent. Exactly at the 1,000-meter mark, literally the exact same depth where the last drop of visible light dies, we find this perfect acoustic storm. It's called the SOFAR channel, which stands for Sound Fixing and Ranging. It is a specific horizontal layer in the ocean where sound velocity is at its absolute minimum.
And here is the mind-blowing reality of this zone. Because sound waves naturally bend toward regions of lower speed, any sound produced within the SOFAR channel just gets trapped there. It bounces back and forth off the faster-moving layers above and below it. It effectively creates a hidden, hyper-focused underwater highway. And that is exactly how those low-frequency whale calls we mentioned earlier can travel across entire ocean basins without losing much energy at all. It's basically a natural fiber optic cable, but for sound. So let's synthesize our top-down journey today. We've seen how the physical transmission of energy entirely defines the living environment of the ocean. Heat from the sun is stubbornly trapped at the surface, creating a warm, thin roof. Light is heavily filtered, stripping away the reds and leaving only the blues, before vanishing entirely by 1,000 meters. But where heat and light fail to penetrate, sound absolutely thrives, bending and trapping itself at that exact 1,000-meter mark to create a hidden global communication network. Which leaves us staring into the dark abyss with one final thought. If an entire acoustic highway exists, completely hidden in the pitch-black darkness at 1,000 meters deep, perfectly calibrated by temperature and pressure, well, what other invisible forces are shaping the deepest, unexplored realms of our planet? Thank you so much for joining me on this explainer today, and keep your curiosity scanning the depths.